All right, well, good morning, everybody. Today, I'm going to take you on a brief journey through my summer project called Nanoparticle Recrystallization. Now, before we run off on our journey, we need to first know where specifically we're going to go. So here's what's going to happen. First, we're going to talk about what the goal of the research was for the summer. Afterwards, we'll go over what we were researching. Then we'll go over why anything I say matters, why anybody cares. Then we'll talk about my methods, my experimental procedure, and the progress that has been made so far. Now, this summer, our goal was to take an aluminum sample and strengthen it. We wanted to improve a few of its properties. Properties like its fracture toughness, which is the ability of that aluminum sample to resist fracture even if there's already a crack in that sample. We wanted to also improve the temperature resistance, the ability of that aluminum sample to perform in a high temperature setting. Additionally, the fatigue resistance, the ability of that material to have a load applied and reapplied repeatedly without that material failing. And the wear resistance, the ability of that material to resist erosion. And we wanted to accomplish all of this through a mechanism called nanoparticle recrystallization. Now, I know what you're thinking, what is that? Well, to understand what nanoparticle recrystallization is, let's start off with something that we already know and understand. Everything is made up of atoms. When these atoms come together, they form crystal structures. Now, these crystal structures are in what you call the micrometer range. For example, this wireless presenter right here, if you really want to, you can measure the micrometers if you'd like. That's not very effective. I would measure this in centimeters. These crystal structures are so small that we have no other choice but to measure them in micrometers. Now, nanoparticle recrystallization takes these micrometer-sized particles and forces them to break apart into pieces. And then it'll take those pieces and force them to break apart as well. And it'll keep doing this. Now, every time these particles break into pieces, they recrystallize into smaller crystals. So, what you have is, initially, this first crystal that's in the micrometer range. Nanoparticle recrystallization will take this crystal and keep breaking it up, forcing it to recrystallize until it goes into the nanometer range. It'll recrystallize until it becomes a nanoparticle recrystallization. Now that we know what it is, who really cares? So what? We have these crystals, they get tiny. What happens? Well, when these crystals get smaller, they get stronger. This is important, and the US Navy cares a lot about this because of something called the Railgun. The Railgun is this electromagnetic weapon that can take a 40-pound projectile and launch it hundreds of miles away at some target at a speed of Mach 7. And when that projectile reaches its target, it'll destroy a building. It'll destroy it, not by exploding, but with kinetic energy alone. At this point, I know what y'all are thinking, and I completely agree, this railgun thing is pretty cool. It is. Now, inside this railgun, what you have are these two 20-foot-long parallel rails. Let's make believe that my arms are these rails. And between these two rails is an armature, and at the back of these two rails, you have power supply. Make believe that's my chest. You have a setup just like this right here. Your rails, your armature, rails, power supply, projectile. Now, this electric current will send electricity through this right rail here. It'll go through the armature and then through this other rail. Now, if we pause for a second and think, if you look around the room and you see, the electrical outlets you can find in front of your desks, those will have about 15 to 20 amps of electricity. Tyco Electronics makes a heart defibrillator that uses 60 amps of electricity to jumpstart your heart. The electromagnetic railgun uses 6 million amps of electricity to take this 40-pound projectile and launch it at Mach 7. That's fast, and that's a lot of electricity. And as we know, when you have electricity flowing through a wire, you will automatically have a magnetic field. So inside this railgun, you've got this massive amount of electricity flowing, and pressure builds up. And right now, this railgun just wants to blow itself apart, but it can't, because these two 20-foot long aluminum rails are bolted down. They can't move. the only thing in this railgun that can move is that armature. And it does, sending that projectile out at Mach 7. Now, how do the two relate? On the one hand, we have nanoparticle recrystallization, which is, again, taking these micrometer-sized particles and breaking them up until they go into the nanometer range. And on the other hand, we have this very cool railgun thing that destroys objects, which I just love. So how do the two relate? Well, if we take a second look at the railgun, we'll see how. Inside of the railgun, as I said before, you have these two rails in the armature, and you have a power supply. Now, this armature that's between the two rails is sometimes an aluminum film. Now, you have that 6 milliamps of electricity flowing through this right rail. It'll get to that aluminum film and it'll say, whoa, 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 hold up now. That aluminum film cannot take that much electricity. That 6 million amps of electricity will force that aluminum film to vaporize into plasma. So what you'll have is plasma rubbing up against these two rails in this railgun. So altogether what you have are this humongous Lorentz force that wants to blow this railgun apart and is twisting and bending these two rails. You have plasma that's rubbing up against these two rails, and what you end up with is rapid rail failure. After firing this railgun just one time, you often need to replace these two 20-foot-long rails, which makes this railgun a powerful but inefficient weapon. That's not good. But what we can do is use nanoparticle recrystallization to strengthen the surface of the rails. Because as I said before, those crystals, when they get smaller, they get stronger. We can hopefully improve the strength of the rails so that when we fire this railgun, we could hopefully launch maybe 1,000 40-pound projectiles without having to replace the rails instead of just one projectile. Now, how do we cause nanoparticle recrystallization? Well, this is what we do. We use something called the surface mechanical attrition treatment. I call it SMAC because I'm cool. Now, over here, imagine an open metal box. Now we have this open metal box, and we throw some 6 millimeter in diameter balls inside of that box. Afterwards, we get a top for that box. And underneath that top, we attach our aluminum sample. We close the box with that top. And what I didn't mention before, left this as a surprise, this box is actually attached to a vibration generator. So it'll vibrate up and down, causing these balls to bounce around. And every time one of these balls hits the surface, it causes these little tiny deformations. And each deformation, each impact helps to break a bond between atoms. When these bonds are broken, crystals get smaller, smaller crystals. Once they reach the nanometer range, make the material stronger. And here you can see the box right there that we use for our setup. And this is a vibration generator, and these two devices here send out an electrical signal that tells the vibration generator how to vibrate. Now, before we SMAT, there's a polishing process and a testing process. Now over here you can see two machines that are used to polish the surface. And what happens is you see these two discs right here on the machines. You put your sample down on those discs, and they rotate and it'll polish the surface. Now that's extremely important. It's extremely important. What you end up with is a reflective surface. You can see your reflection. That's very important, not because I can look at the reflection and see that I'm handsome, but because of one of the tools that we use in the testing process. So just to reiterate, before we SMAT, we polish and we test. After we SMAT, we test again so that we have results to compare. Now, in this testing process, we have the scanning electron microscope and the MTS machine that we also use a furnace with. Now, the scanning electron microscope allows us to get these high magnification images of up to 650,000x. And what that will let us do is see if we are actually decreasing the size of these crystals, if we're actually bringing them into the nanometer range. The SEM will allow us to see that by sending these secondary electrons at the surface. And if you have a polished surface, those electrons will bounce off and you'll get a good image. Without a polished surface, you'll get a poor image and you won't even be able to tell if you are actually decreasing the size of these crystals. The MTS machine is basically a stress tester. What we can do, you see these two little hands here, they'll grab onto the surface and they can pull it, or you can put these two barriers here and you can run compression traffic tests. You can also run some torsion tests as well, and there's a strain gauge that'll measure how much this sample is deformed at a specific load. Now, the furnace allows us to test the temperature resistance of the material by doing all the same tests as the MTS machine, except this time in a box that heats up to about 1200 degrees Celsius. Now, our progress so far, what we've done. I've done plenty of small tasks, but the biggest things that I've done is, first of all, I've completed SCM training. I can go and use the standing electron microscope whenever I please. Additionally, I've come up with a new design for the vacuum chamber that we have in our lab. Now, if you see here, this is a vacuum chamber. I think it looks pretty cool, but it has some problems. First of all, there are corners. When a ball hits one of these corners, it'll slam up against multiple surfaces, decreasing the amount of energy that's in that ball. When you decrease the amount of energy in that ball, you decrease the amount of energy with which that ball will impact that surface, which is bad. We need that surface to be impacted with a high amount of energy so that we can break those bonds. Additionally, you have only two types of surfaces. You have your vertical surface and your horizontal surface. And what we want in this chamber is for the balls to bounce around in a random motion. We can improve the shape of these surfaces so that we can have more of a randomized motion inside of this box here. Additionally, there's nothing keeping any airborne impurities out of this box. I solved that problem. Came up with two new designs that took care of all of the things I mentioned before. The first one's called the Icarus. The second, the Igloo. I didn't name them. Don't ask me about them. But here you can see the sample is attached to the top, and this bolt here attaches to the vibration generator. So that sample right there will vibrate up and down. It eliminates those flat, non-rounded edges, those flat, non-rounded sides. Both of them do. Additionally, there's a hole right about here and a hole right about here that allows you to attach a tube that we can turn this into a vacuum chamber once it's sealed. Suck out all the oxygen and whatever else is inside of the chamber. So, altogether, at the end of the summer, my team wants to be able to confidently and fully say that we have taken an aluminum sample and strengthened it through the use of our surface mechanical attrition treatment. I'm Jeremy Marshall, and this concludes our journey through nanoparticle recrystallization. Thank you.
Time for, do we have time for questions? At least one question we have time for.
Oh, yes.
Yeah, well, you spent a significant amount of time talking about railguns and railgun blowing things up applications.
Yeah.
Is there any other real-life productive applications of this that doesn't involve particularly blowing things up or something?
Oh, sure there is. I mean, it's not as cool, but certainly there is. What you have are pipes, and when you have, I think, high temperature, whatever, running through these pipes get worn, there's erosion in these pipes. We can also use nanoparticle recrystallization to strengthen these pipes so that you don't have to replace these often. So that'll be one way you can use this mechanism.
So is this essentially just a highly specialized kind of shot peening process? Or are there other differences aside from just kind of learning something different?
The difference here is that, actually this is very similar to shot peening, but the difference is what's going to happen after we know that we can take this aluminum sample and decrease the crystal sizes. If you can go back a little bit, and if you take a look, in that box that I mentioned before, we have the balls. Now, our current setup uses aluminum balls because we're using an aluminum sample. In the future, what we want to do is take those balls out and instead use tungsten carbide balls. That's going to be the new part. What we're hoping to do is get this tungsten carbide to diffuse into the aluminum surface. So that'll be the new part. So if that answers, does that answer your question?
Kind of, I guess the point of my question would be, I mean, shot peening, typically you're looking at getting surface stresses and something to avoid cracking and things like that. Are you looking at, does this do anything with, getting surface stresses, or is it mainly just breaking bonds?
No, it's mainly just breaking
Okay.
bonds, yeah.
So it's just a kind of a different process.
Sorry, in the interest of time, we'll move on to the next one. There's going to be a break after this talk, so we'll continue.